Okay. Let's see. Three. You take it again.
I'm coming in more of the.
That's right. Gotta keep reminding me. Okay, so let's let's look at chapter 6. Let's chop things off over there, but I'm not going to get up on the table and fix it. The next exam, exam 4, is just on the one chapter, chapter 6. And we're going to look at thermochemistry. What do we mean by thermochemistry? Well, by now we should have a pretty good idea of what chemistry is. Just study chemistry where it relates to heat, energy transfer. That's what the thermo stands for. There are, in fact, I can't think of any chemical reaction that doesn't involve a transfer of energy. There probably are some, so I'm hedging my bets. So what is energy? Energy, by definition, is the capacity to do work or to produce heat. If it does work, then it's useful. I mean, it's going to be of a benefit to somebody. If it just produces heat, then it might be beneficial, and it might not. If we mean it to produce heat, then yeah, it's beneficial, like gas burners. So it keeps working. Flashing red. There it goes. It's probably just right on the edge. It needs to be blown out. Yeah, it's got, probably got dust in there. So, the law of conservation of energy applies here. It just says that energy can neither be created or destroyed. It can only be converted from one form into another. And that basically is the first law of thermodynamics. Thermochemistry is sort of is our way of easing you into thermodynamics, because if you hit you smack in the face with thermodynamics, you'll just throw up your hands and walk away. So this is the way that we ease you into it. And the law of conservation of energy is also stated as the first law of thermodynamics, which says that the total amount of energy in the universe, now the change in the total amount of energy in the universe is 0. Everything all together in the universe, the amount of energy that changes is 0. So that just means that we can convert it into one form or another, but you can't create it or destroy it. And that's true in a general sense, but ever since Einstein came along, we found out that matter and energy were interconvertible. E equals mc squared. So you can take a small amount of matter and convert it into a huge amount of energy. That's why atom bombs and nuclear power plants work so well. But that's not our topic today, so we'll move on. So we can divide energy into two forms, either potential energy, which just means that it's there and accessible, but we haven't used it yet. So that's potential energy, and Sometimes I'll write it this way. The book might write it, no, excuse me. Book might write it like this with maybe a P or a PE, or potential energy. And it's due to one of two things, or it could be both. Position, so the potential energy could be based on position or on composition. Composition is like nitroglycerin. It's got a lot of energy built into that molecule, and all you have to do is just disturb it a little bit, and you get more energy than you bargained for. Right? So the energy, compositional energy, is like explosives, and the energy is contained within the molecules, and you release it. Whereas energy of position has to do with where the object is in a gravitational field, like near the surface of the Earth. So if this is the Earth, and you have an object here, all you have to do to store energy in that object is to move it further away from the Earth. It takes energy to do that, right? To blast a rocket off, you need to release energy. Or you can just lift this up in an elevator and go up to a certain height. And the difference in height here, plus the force that's required, well, not force, times the force that's required, is the stored energy in that object. Right? What do they say? It's not the fall that kills you, it's the sudden stop at the end. If you jump out a window, they heard the guy saying as he was falling, it says, so far so good, until he hits the ground. And then you get all that energy back, right? So if you turn that object loose, it'll fall until it hits the Earth's surface, and all the energy that was stored in it before is suddenly released when you hit the ground. Now, if the object is sturdy enough, it'll withstand the impact. But if it's not, all that energy released will just blow it apart. So you can have potential energy of due to its position or due to its composition. Kinetic energy, on the other hand, it might be written this way, is due solely to motion. If something is moving, it has kinetic energy. Right? So all the molecules in this room are, at this temperature, they're furiously moving. Right? We did that calculation, I think, at the end of last chapter. How fast are they moving? On average, they're moving about the speed of sound. Okay. So anything that's moving has kinetic energy. The only thing that doesn't have kinetic energy is any object at absolute zero. Right? If there's no temperature, and of course it has to be sitting still. If it's moving, then it can't be at absolute zero. So it has to be sitting still. And the kinetic energy of that object will be zero. But we can't do that. It's a physical impossibility. So those are the two types of energy that we account for in any physical or chemical process, potential or kinetic. And you can calculate the kinetic energy of any mass, M. Of course, standard units would be M is in kilograms, and velocity is in meters per second. Right? So the kinetic energy units of measure, because of this formula, mass would be in kilograms, velocity would be in meters per second, but they're squared, right? So the energy units would be kilogram meters squared per second squared. And one of those is equal to 1 joule. That's the interconversion between the SI units and energy joules. Because because of that formula. Okay, so if this object A has certain potential energy, it has more potential energy than B. So something's holding it up here. If we turn it loose and it smacks B, then if there's no loss of energy to any other forms, then all of that energy will be transferred to B. And A will be sitting here, and B should be back up at this height, right? Right? If we can't create or destroy energy, and we've accounted for all of it, in this case, just for potential energy or kinetic energy of motion, then all that energy should be transferred to B, and B should have motion enough to get back up to this point. Right? But this is what actually happens. B only rolls up a little bit. Right? So the energy that A had is only partly transferred to B. So where did all that other energy go? Turned it into heat. Right? The object B, for the most part, B just got a little warmer. So some of the energy is reconverted into potential energy of position, and the missing amount that would have put it up here is converted into heat. In fact, if you have a sensitive enough thermometer, and I take silly putty, right, hold it up here, measure the temperature. Of course, I have to have insulated hands, and drop it. When it hits the floor, stick your probe in and measure it. It will get warmer. Not by a lot, but it's measurable if you have the equipment. Okay. So how do we know that there's heat in an object? We can't measure absolute heat because we don't have access to absolute zero, right? There's nothing that can make it to absolute zero. Think about it. How do we get things to become colder? We transfer the heat from this object to some other object that's cooler, right? So that's how our air conditioners work. We make our house a little cooler in the summer because we take the heat out of the house and dump it outside. Okay. So how would you get something down to absolute zero? You can't, because there's nothing colder than that, right? So there's no heat sink that's colder than absolute zero. That's why you'll never get there. It's theoretical. Now, there are some scientists that would argue with me, said, oh yeah, we're down to absolute zero with this one little molecule. All we had to do was find out where it was, touch it with a laser, and it stopped. Technically, we're at absolute zero. Okay. Whatever gets your grants funded. Okay, so back to heat. How do we measure heat? We measure heat in terms of a difference in temperature. So if I drop that silly putty again, the only way that I can tell that it's warmer than it was is the difference between what I measured before and what I measured after. And that indicates a transfer of energy or heat. So you need two heat measurements. And in order to transfer the heat, one object has to be colder than the other because heat always flows downhill. It always goes from the warmer to the colder, never the other direction. Spontaneously, heat transfers from hot to cold. Now we can force it to go back the other direction, but in order to do that, you have to couple it with something that's colder and then dump that heat into your heat sink. So it can be a cascade effect. And, well, I won't belabor that point anymore. So let's get some more definitions out of the way here. So what is work? Right? If we have some useful form of energy and we use it to move an object, by applying a force, and the force acts over a certain distance. So a force acting over a distance is work. Okay? If I push on this wall, I'm applying a force and it's costing me energy, but the wall's not moving. So I didn't do any work. Let's see, so what would the units be here? The units would be meters for distance, and the force is not kilograms, that's a mass. The force is a newton. Now the newton is a calculated value. It's based upon SI units. And we'll talk about that. Though actually it's kilogram meters per second squared is a newton. Right? So when you multiply kilogram meters per second squared times meters, you get kilogram meters squared per second squared, which is what? A joule. So work is also measured in joules. Right? So if we can convert all this work into heat, we could get a certain number of joules. Or if we converted that work into motion, we could get kinetic energy, which is measured in joules. So see, they're interconvertible. Okay, so that's technically work, is a force acting through a distance. Now, functions. What do these functions mean? Remember when we were talking about gases, I hope I alluded to before, after, and state. Right? What is it right now, or is it a change that occurs? You're given initial conditions and then changed conditions. Those are the two approaches to solving one of our gas problems. Right? So the state function simply says, this is what it is right now. This is its current state. Doesn't matter how it got there. Some functions are state functions. Doesn't depend on how you get there. Others are path functions. They do depend on the path you take to get where you're going. Perfect example. If we go from Charleston to Beckley, your elevation is going to probably increase by, well, I don't know what, 15, 16, 1700 feet, something like that. So you could either go straight up to that height, or you could take the long way around. Now, how much work is it going to take? It takes a certain amount of work, a force acting against a distance of height, and then that's only vertical, then you have to go horizontal. Or you could take the long circuitous way, in which case it would take less force, but it'd take you longer to get there. And the amount of work expended depends on the path that you take. It'll be a different value for taking the long circuitous route than to take the shorter route. Or maybe if you come up the turnpike, it's one way. Or if you go, go upriver and then to Montgomery and then go back up through the hollers and then back around through Oak Hill and then back down to here. It would take more work probably. So that's a path function. The path does matter. And work is one of those path functions. How much work is expended. Now, the difference in energy between where you are at Charleston, where you are here, the total amount of energy stored in the process of moving from there to here is a state function. It doesn't care how you got there. Okay? I know those are difficult concepts. They've always given me trouble too. Just repeating over and over again, they always sink in. more definitions. We need these definitions so that we can talk the same language. And the first one is, what is a system? System is whatever you define it to be, right? Or whatever the problem defines the system to be, right? If the word problem you're reading interprets the situation in some form or fashion that gives you information about what the system is, then you take the problem. But if it gives you a lot of freedom, then you can define the system. So our system is whatever whatever the problem says it is, or whatever we say it is, and everything else is surroundings. Okay? Now, the comparison of the two and what happens between them depends on the type of boundary that is between them. The surroundings could be everything else in the universe, right? Our system separated from the universe. Or we could define our surroundings and limit the surroundings that are considered in the problem. In which case, this would be the total to distinguish it from the universe. Okay? Now, if we say the system is open, then we can transfer mass and energy freely back and forth between the surroundings and the system. That's an open system. Okay? We rarely are interested in that kind because it's difficult to describe it, right? But they do exist. Right? A closed system is one in which mass does not cross the boundaries. Only energy can cross. So this would be a closed system. Okay? The only other possibility is isolated. Isolated system can transfer neither. You can't transfer matter, you can't transfer energy. This is isolated, which means this is insulated from the surroundings. Nothing crosses that boundary. Now, where would we use something like that? Well, we're going to do it when we get to our thermochemistry lab. We have a couple of styrofoam cups we use to make our calorimeter. I'll talk about that more later. But it isolates our system from the surroundings. No heat transfer, no matter transfer. Everything that happens inside the calorimeter. Okay. That's an isolated system. Closed system will let energy transfer. Okay. Now there's some conventions if we're going to talk about energy transfer. Everything is relative to the system. And what I mean by that is the sign that's on the numbers, right? If we transfer so many joules into a system, it's a positive value. Because relative to the system, we're adding energy to the system. Right? So if we go this way for energy, it's positive. If we go this way for energy, it's negative. Okay? Everything's relative to the system. Energy in plus energy out, negative. Now, when that happens, if there's a chemical reaction going on here and we measure a transfer in energy, if the energy comes into the system during the reaction, that's endothermic. Endo meaning into. Endothermic, into heat, into the system. If it gets warmer, if you measure a transfer of energy out of the system, it's negative, and that's exothermic. Okay? So let's see if we got a handle on this yet. So, is the freezing of water an endothermic or exothermic process? What you have to do first is define your system. So what's your system? Our system is the water in some container. That's our system. And the surroundings will transfer energy one way or the other. Right? So if we've got liquid water to start with, and it becomes solid water, do we have to add energy or remove energy from that water to make it freeze? Mm-hmm. Right, so energy is going this way, which means it's negative, which means it's exothermic. So freezing water is an exothermic process. Define the system, define the surroundings, then which way is the energy flowing? And this is exothermic. Okay, so let's try these on for size. Define as exothermic or endothermic. Your hand gets cold when you touch ice. The system is your hand. And it's getting cold by transferring heat which direction? Away from your, out of the system, right? So that's an exothermic process. Okay. Ice gets warmer when you touch it. Okay, so the ice is the system, and you're measuring the movement of heat by how it feels on your hand. So this is your system. If it gets warmer, which way does the heat have to go? Into it. That's endothermic. Water boils in a kettle. Okay, so our system is the water in the kettle, and we're adding heat to it, and in order to boil it, the heat goes into. So that's endothermic. Water vapor condenses on a cold pipe. So we're interested in what happens to the water vapor. It's changing from a gas to a liquid. So in order to do that, we have to extract heat from it, right? So that should be exothermic. And ice cream melts. It's going from a solid to a liquid, right? In order to do that, you have to add energy to it. It's endothermic. Okay. Tricky concepts. Okay. Let's see. Let's define the system and what the surroundings are, and then give the energy transfer. So what's our system? Methane is burning in a Bunsen burner. The system is actually just the methane mixed with air, because it's not going to burn unless it's got access to air. So methane and air is actually our system. And when it burns, what does it do? It releases energy from the system as it burns. Energy moves out. So that's negative exothermic, right? Oops. Doesn't give the answers, so we have to make them up as we go along. Water drops sitting on your skin after swimming evaporate. So the water drops are our system. And as they evaporate, they have to extract energy. They need energy to evaporate. The energy comes from your hand, which is the surrounding. Right? So the water drops are the system, energy transfers into them, which is endothermic, the positive value. Okay. So hydrogen gas and oxygen gas, they react extremely violently. In fact, they release a lot of energy. That's one of the ways that we got the space shuttle into low Earth orbit. Had that big orange tank on the outside. It was actually two tanks in one. One of the tanks is liquid hydrogen. Another tank inside was liquid oxygen. You combine them in the engine. You don't combine them outside. You do that, you get the Challenger disaster. But once you put them in the engine and ignite them, then they create water, hydrogen gas, oxygen gas, makes water, and releases that energy. So here we have hydrogen gas and oxygen gas producing water. And it's going to be gas because it's so hot. Let's see, let me balance it first. 2 here and 2 here. Okay, so when we combine these, we get energy, right? It's exothermic. So the energy is a product, right? It comes out over here. We write it like that, change in heat. So that means that this energy coming out over here had to be somewhere over here. That's what we're saying with this sign. We're saying everything over here used to be over there in some form or fashion. Right? We rearranged the molecules, but we also, that heat used to be over here. So what that means is these two together contained the energy that we now have over here, free. So these were higher energy together. And this one is lower energy because now it's outside. Okay. So the mixture of hydrogen and oxygen is the lower energy, the higher energy, and the water itself is the lower energy. And it's useful to think about chemical reactions in those terms, particularly in this chapter, because that's one of the driving forces for a reaction. The products sit at lower energy than the reactants. Okay. Now you can drive the reaction backwards, right? We could make this one go back that way. We just have water and 2 electrodes with direct current in them. Of course, we'd need to add maybe a drop of acid so it'll conduct the current. But as the energy transfers through, we add that energy back in here and split it into hydrogen and oxygen. And you can do that. If you get a little water and maybe put a drop of lemon juice in it, and then get a 9-volt battery. Just drop the battery in the water. And before too long, you'll see bubbles forming at the electrodes. One of them is hydrogen, one of them is oxygen. So you can drive a reaction backwards, but spontaneously, it wants to go that way, toward the lower energy state. Okay, I mentioned this earlier, thermodynamics. And this law, in thermodynamic terms, is just stated as the change in the energy of the universe is equal to 0. You don't add energy, and you don't create energy. You don't create energy, you don't destroy energy in the process. You just change the form. Now, that being said, some energy is what we say higher quality. Right? So in the process of like running your automobile engine, you're degrading the value of the energy from octane or gasoline in your tank to lower energy products like carbon dioxide and water, ideally. But in those engines, we produce other things like oxides of nitrogen, incomplete combustion, carbon monoxide, all those. But they're all lower energy state than the original gasoline in the tank. Okay, so now we've defined system and surroundings. Let's do this, and this, and this, so we can talk about it again. And there's another concept. It has to do with internal energy. So how much energy is in your system? And when we talk about internal energy, it's a similar concept to talking about heat transfer. You only measure it in terms of change in temperature or work done. Okay, so force applied through a distance is work, or a change in temperature indicates a change in heat. Those two factors together define the change in internal energy of our system. So here's the change in internal energy, delta E, and it's equal to the Q, which is heat. It's our small letter for heat, plus any work that was done. Right? And the signs are important. Right? So we talked about heat. So if heat transfers into the system, Q will be positive, right? And if heat transfers out of the system, it's negative, and that affects the total internal energy. Similarly with work, right? If we do work on the system, the value of work is positive, right? It's all relative to the system. We do work like it's a gas, like we squeeze it. We're doing work on the system, positive. Or if we allow the gas to expand against the surroundings, the system is doing work on its surroundings, and that's a negative value. Okay? It's like in your internal combustion engine, the pistons move up and down, right? So when the piston is moving up, we're compressing the gas and doing work on the gas. Right? So that in that case, the work is positive. But when we spark it, it explodes. The system then is exothermic, and that energy is released and causes the gas to expand, causes the piston to go down. Now the gas is doing work on its surroundings. And at that point, W is negative. Okay. All right.
Between the internal energy of a system and the energy flow, dynamics gives the relationship between the internal energy of a system and the energy flow into and out of the system. This example shows a system where heat enters and work is done by the system. Internal energy remains constant if there is no friction. If instead of adding heat, we do work on the system by compressing the piston, then energy will flow out of the system as heat. The internal energy is again constant. Take note of the sign conventions for Q and W. The signs of Q and W are positive when energy enters the system. Here we have a system in which a chemical reaction is taking place. What are the signs on Q and W in this example? Is there a change in internal energy?
Well, let's see. The piston is rising. So as the gas expands, we're doing work on the surroundings, so that would be negative, right? Okay. How about Q? Well, which way was Q going? Is it going into the system? It's out of the system. Out of the system. So that one's negative also, right? Okay. So the change in E has to be negative. Both of them are negative. Right? So the change in internal energy is decreasing in the system because it's moving out. So So overall, the change in internal energy is negative. If we had a process, let's just theoretically, that had both positive values, right? Work was being done on the system and heat was being added to the system at the same time, then we would increase the internal energy. It would be positive, right, in those circumstances. What if one was negative and one was positive? It depends on magnitude as to whether the change would be an increase for the system or a decrease. So in those cases, it's conditional. I have to retake control. There we go. Okay. So these quantities we're talking about, whether it's heat or work, are the same as any measured quantities. There's a number associated with it, given the magnitude of the change, and there's a sign. Actually, there's a unit of measure. I always leave that one out. So you can have the number, which incorporates a sign, which indicates the direction of flow. And there's a unit of measure, and we mentioned that earlier. It's usually joules. Or, if it's large enough, we might decide to use kilojoules or 1,000 joules as a unit. And some reactions are so exothermic or endothermic that it's more convenient to measure it in kilojoules. Particularly those combustions. They tend to release a lot of energy. Okay. So in an endothermic process, Q is positive. Heat's moving into. In an exothermic, Q is negative. Heat's moving out of the system. We're just hammering this point home. The sign always reflects the system's viewpoint. What does the system see? Is it coming in or is it going out? And in those terms, if the system does work on its surroundings, work is leaving the system, it's negative, and vice versa. Work would be positive if work is being done on the system. Okay, this, let's see. I put a lot of detail into this one just so that you have a record of it. But the simplest way to describe work in terms of a system is let your system be a gas, a confined gas with a frictionless piston, right? That way you can measure a height, right? The distance that the piston moved, right? There's our D value for force times distance. Right, so we got that one. Now we need to find out, how do you measure the force? Well, if the gas is under constant pressure, we know that pressure is force divided by unit area, right? So if this is our unit area, that piston, it's easy enough to calculate the area of a circle. And the pressure is constant. So if pressure equals force times area, then force would be pressure times the area, right? So this is going to be, this value here is going to be pressure times the area of that piston. Okay? So there's our force, pressure times area. We substitute that in. What is, let's see, we're actually changing the volume though, right? Because we're going from here down to here. So there is a change in volume. And the change in volume is the distance times area. So the distance in terms of delta H here, actually D and delta H are the same, is relative to change in volume divided by area. So this one is going to be change in volume divided by area. There we go. So we got force here, we got area here. Notice that the area cancels. One's the numerator, one's the denominator. So it's pressure times change in volume is a measure of work. For constant pressure, if the pressure does not change, then all we need is a change in volume times that constant pressure, and that tells us how much work is either done on the system or by the system. Right? If we let the gas expand under constant pressure, then we just reverse the sign. Okay, let's see. So here's the problem. Now that we've defined the amount of work, pressure times change volume, we've got a problem with sign because pressure is positive and a change in volume, we moved from, well, change in volume we're saying is a decrease. We went from large volume to small volume. So that's a decrease in volume. So this would make work negative.
I think the volume increased. It went. It increased.
Oh, did it go?
Yeah, it
Go the
increased.
other direction? Excuse me. Oh, we let it increase, didn't we? Right. So the volume increased. Okay. So that makes the work value positive. Okay. Pressure is positive. Change in volume was positive in this scenario, right? So the work is positive, but what does positive work mean? It means work was being done on the gas. So if we go from this to that, I was going backwards. Sorry. We let it expand, and we're saying work is positive, then the sign's wrong, right? So the sign tells us that we're doing work on the gas when it's not, it's the other way around. By our convention, the gas is doing work on its surroundings as it expands. So we have to introduce a fudge factor. Right? So actually, we put a negative there. Now the units are correct. The sign is correct. Under this scenario, the gas is doing work on its surroundings as it expands. So that's why the negative sign is there. Just to be sure of that, the convention is consistent. Now, if we multiply our standard values for pressure as atmospheres, right? And volume is liters. So we've got a liter atmosphere, but that's not equivalent to joules. We need a conversion factor, right? So the actual value here at this point is liter atmosphere. But if we want to convert it to joules, we need this equivalence. 1 liter atmosphere is actually equal to 101.3 joules. Right? So if you were to do this little experiment and calculate liter atmospheres for that work, before you could compare it with any other energy transfer or any work calculation, you have to convert it to joules. And that's what this is. So 1 liter atmosphere is equal to 101.3 joules. That should be in the useful information. Let me just check it to be sure. In your review document, so we look at the very back. Yeah, there it is. Middle of the page, middle of the second column. 1 liter atmosphere is 101.3 joules. Okay, how are we doing on time? 1:20. We might have to postpone the lab today. That's okay. Instead of doing Boyle's Law today, we'll do it next week. Okay, which of the following performs more work? All right. So let's see, we got to do our calculation for work. Let's see, we're going from under 2 atmospheres constant pressure, we're going from 1 liter to 4 liters. So here's the formula. Okay. So the first one, what are our conditions? The pressure is 2 atmospheres, right? And the initial volume is 1 liter. Okay. 1 liter. Final volume is 4 liters. Okay? So remember when we say delta something, it's always final minus initial. All right, so delta V here would be 4 minus 1. Equals 3 liters. So our calculation is minus 2 atmospheres times 3 liters, which is minus 6 liter atmospheres. That's for A. For B, what are our conditions? Let's see, we've got 3 atmosphere pressure. Okay. And our initial volume is 1 liter. And our final volume is 3 liters. Okay. So our difference here is final minus initial, which is 2 liters. And our calculation for work is minus pressure, 3. And then the change in volume is 2. So that's equal to negative 6 liter atmosphere. Same. Anybody see that one coming? So it's the same amount of work, and the work being negative means that the gas expanded under constant pressure doing work on its surroundings because they're both negative. Okay? And you need to pay attention to this convention, initial and final, because you're going to subtract the initial from the final, regardless of the sign. If it were the other way around, if this were 4 and that were 1, that would give us a negative 3 liters, and in this calculation would give us a positive value, which means it's going from 3 to 1, and the surroundings are doing work on the gas, which means a positive sign for work. Okay. All right. Everybody got that one? Okay. Just checking sure I'm recording. I hate it when I forget to record. We good yet? Still working. Are you writing in your pad? Oh. Is that a special stylus?
Yeah.
Okay. Okay. waiting. Don't forget, I've got some labs graded too. Thanks very much, Satchel. Okay, so let's take this next one and see if we can make sense of it. Determine the sign of delta E for each of the following. All right, so what do they mean? Delta E, internal energy, is equal to the heat transfer plus the work transfer. Okay? So, an endothermic process that performs work. Let's see, A, endothermic process that endothermic and performs work. So, what does that mean? Endothermic is relative to the Q value. And in this case, endothermic means Q is positive, right? Endothermic, transferring energy into the system and performs work. So work is being done on the surroundings, which means this one is negative. Right? So now that we have a positive and a negative, we don't know the sign of this one until we're given relative magnitude of each one. Right? So into this situation, when work, the absolute value of work, is greater than the absolute value of Q. So the magnitude of the values are this, and then we apply the signs to them. Right? So work is negative, and Q is positive. So the negative exceeds the positive, right? That means delta E would be negative. So if it's the other way around, if this one is less than this one, right? And this one is negative and that one's positive, then this one is greater than that one. Now delta E is positive. Okay? It helps to draw it out like that. Right? If you try to reason it in your head, it just kind of flies around and doesn't make any sense. But it helps to think on paper, so to speak. Okay, how about B? In the work, let's see, an endothermic process performs work. Work is done on a gas, and the process is exothermic. Okay, and exothermic and let's say receives work. That work is done on the gas, but it's exothermic, which means it's losing heat. So that's negative, and this is positive. Okay. Now, if we look at the same conditions for this one, where we have W greater than Q, then if W is positive and Q is negative, then the sum of the two has to be positive. So we're increasing the internal energy by this process. And under the other circumstances, if work is less than absolute value of work, that's why these two bars on either side, if this is still negative, and that's still positive, then if this one's bigger than that one, now the change in internal energy is negative. Okay? See if I got them right. Negative, positive, positive, negative. Well, maybe I didn't get them right, but I agree with the slide. The reasoning is the same. No, it's right. Take my word for it. Okay. So up to this point, we were using Q's and W's. W for work, Q for heat. And now we're going to introduce a new term called enthalpy. Enthalpy is often referred to as the heat of reaction. But strictly speaking, it may or may not be equal to Q. It depends on the circumstance. So it's helpful to think of delta H, or change in enthalpy of a reaction, as different than Q. This is the actual amount of heat that is transferred into system or out of a system. That is a true measured amount. And is one of the two ways of changing energy, changing the internal energy, Q or W. And that's why we write it this way. Right? But what about enthalpy? What do we mean by enthalpy? Enthalpy should be thought of as more potential. Kind of like, what's the potential energy of an object that's moved from the surface of the Earth to a mile high? We've increased its potential energy. And if we let it drop, hit the ground, all that energy is going to be transferred, converted into heat, more than likely, assuming it doesn't break apart. So the potential of the reaction is delta H. Similar to internal energy. And remember we mentioned state versus path functions. State functions include internal energy, doesn't matter how you get there. Enthalpy is also a state function. Since it's a potential measurement, we don't care how it got there either. Now, how do these things relate to one another? Well, the change in internal energy can be related to the change in enthalpy. Right? They're the same units, joules. The only difference is what happened to the gas, pressure volume change. Right? So if we change this value, pressure times volume, whatever that happens to be, add it to internal energy, then we get enthalpy. Now, if this value is negative relative to that value, then the enthalpy will be less, and some of the enthalpy will be lost in terms of a pressure volume change. Okay, that's all that means. It's related to the internal energy, but it's not necessarily equal. Now, when can we say that it's equal? Well, let's insert what delta E, internal energy change, is equal to. It's equal to Q plus W, right? So that's all we did. We just inserted that value, those two values here for that one. If the process takes place at constant pressure, then we factor the pressure out because it's not changing. Only the volume is changing. Right? So now we're looking at this. This is the only difference between the two. Since pressure is constant, if we hold it constant, artificially speaking, then we get this expression, where this is internal energy, and this is a pressure volume change. Okay? So now that we know that W is also equal to constant pressure times the change in volume, right? So we say, substitute this value in here, then we get a minus P delta V plus a P delta V. Okay? Now that delta V, the delta V has to be the same in these two. So this and that combined together cancels out, right? It's zero. So the only reason that I'm doing this exercise here is to show you that if you hold the pressure constant, don't let the pressure vary, then delta H is actually equal to the transfer of heat measured by Q. Okay. So while this is a path function, the amount of heat does depend on the path. As long as we hold the pressure constant, then this path function, Q, is equal to this state function, delta H. And that's what chemists do when they study reactions. They study them under constant pressure so that they can equate the two. So if we measure the change in Q by a temperature difference, then we can equate that to the potential delta H for that reaction. Okay? I know that's kind of, it's like I'm beating a gnat with a hammer. But it is true. It's easy to get the two confused. And just remember, if you remember anything, the delta H and Q are equal only when pressure is constant. Okay. So here's an example. You're studying a process that takes your system through these changes from P1, V1, T1 to P2, V2, T2, right? We know what those relationships are based on our gas laws. That's not a problem. There are many different paths to getting there, right? If you let the pressure change from P1 to P2, but you let it go up like this, and then it goes down, and it goes back up and down. That's definitely a change in path. That's a path function. Same thing with volume, temperature in the beginning, and temperature in the final. It can go through different changes also. And along each one of these paths, we will note a different Q and a different W in the process. Because as you change these various things, the Q is keeping track of all those changes. Let's put it that way. How about that? The Q and the W are keeping track of those changes. But no matter what path you take, eventually you end up at a difference in what was the heat content before, what was the heat content after. That's delta H. So delta H is a state function, whereas Q and W are path functions. If we let the pressure remain constant, of course, during this process, then we can say that Q and delta H are equal, even though one is a path and one is a state function. They are equivalent. So this is very convenient. State functions are useful in this particular case because if we want to know what is the enthalpy change for this reaction, all we need to know is what is the enthalpy of the products minus the enthalpy of the reactants. And of course, these have to be measured against some standard, right? And we'll talk about that later. Yeah, let's talk about it now. So the products and the reactants are measured against standard states. Standard states of temperature and pressure, standard states of reactants, which would be elemental, implies 0 delta H. Right? So if it's a metal like gold, solid, under standard temperature pressure, that's your 0 state. Right? Or if you have a diatomic gas, that's your elemental 0 state. Okay, so these products and reactants enthalpies that are listed in tables, right? You don't have to calculate them; they're listed. You use them to calculate. Then the reactants or products, if they're elemental like this, their values are 0. The only ones you have to be concerned with are the compounds. Okay. And we'll talk about that in more detail later. I just thought I'd give you a taste. Okay. So just to restate, constant pressure, these values are equal. So all we need to know is what's the enthalpy of products, add those together minus the enthalpy of the reactants, and you can calculate the delta H for a reaction. Now you can measure it, right? You can measure this delta H. All you'd have to do is conduct the experiment at constant pressure and measure the transfer of heat into it or out of the system, and you can measure it. But suppose we're too lazy, we don't want to do that. You can calculate it. Calculate the expected delta H for a reaction. It's also valuable if you don't know what to expect out of that reaction. Maybe that reaction is going to be violent. And this will tell you whether it's an endothermic or exothermic reaction. Right? So if it's exothermic, extremely exothermic, you want to take precautions. And the only way to know in advance is to do the calculation beforehand. Okay? So it's a safety feature too. Okay, here's one. Everybody's either heats their home with propane or has used a propane grill, right? That's what this is, propane. We're going to burn propane in air and produce carbon dioxide and water. And it's exothermic, there's your negative, right? Delta H is the same sign. The enthalpy, if it's negative, is exothermic. If it's positive, it's endothermic. And it's 2,000 kilojoules, right? So actually that's 2 million joules. Okay? So this one produces a lot of heat. And of course, if you've ever used a propane grill, you know that intuitively. So if all of the heat comes from the combustion of propane, right, in this case, calculate the delta H for, now this is for that reaction, right? Calculate the delta H if only 5 grams of propane is burned in excess oxygen, right? So here's our reaction. What are we talking about here? What type of problem is this? Stoichiometry. Right? That evil, ugly word. Stoichiometry. Okay. So we're given 5 grams of propane and excess oxygen, which makes sense. If you burn it in the air, there's plenty. So, and the delta H for this reaction here is minus 2221 kilojoules. So from that reaction, it produces kilojoules as long as 1 mole plus 5 moles equals 3 moles plus 4 moles. That's what that's saying. So it's like minus 2,000 kilojoules per mole of methane, propane. Or in this reaction, it's that many kilojoules per 5 moles of oxygen, or per 3 moles of CO2 produced, or per 4 moles of water produced. Okay, that's what that means. So where do we go from here? Well, if you got this many grams, how many moles does that represent? We need a molar mass for propane, don't we? Right? And then 8 hydrogens. So what would that be? That's just 3603. And that's 8.08. So 8 plus that is 1. And the 1 goes up there. And 8 plus this is 14. And 1 and 24 is 25. Is that right? 254, 11? No, that's not right. It's ridiculous. Can't be. Let's see, 8 and 8.
It's 44 point. Yeah.
Okay. So this is grams per mole. We'll find out how many moles were reacted here. Right? We just need to multiply that with grams on the bottom, right? Moles on the top. So 44 into 5. 0.11. 0.1134.
Yeah.
1134 moles. Right? So, if 1 mole produces this much, how much does that produce? This is moles of C3H8. So this is minus 2,221 kilojoules per mole of C3H8. We'll cancel that. Multiply 0.1 times minus 2221. And I get 252, roughly, kilojoules is how much heat is produced by 5 grams of propane burning. Okay? The trick to this problem is recognizing what the relationship of this is to the overall reaction. Right? If we had said 5 grams of oxygen, then it would have been this many kilojoules per 5 moles of oxygen. That would have changed this value. Right? Instead of 1 mole of this, it would have been 5 moles of that in order to do the calculation correctly. Oops. Okay, calorimetry. What do we mean by calorimetry? Calorie refers to, actually, it's, I don't know if it's Latin or Greek. Well, most of Latin was derived from the Greek. They stole everything from the Greeks. But calorum refers to heat. So what we're doing in calorimetry is actually measuring the heat of any process. And we do it using an isolated system. Remember I said open, closed, isolated. Closed system where you allow energy to transfer across the boundary between the system and the surroundings. You don't let matter cross the boundary. That's an open system. Closed system, you allow heat to transfer. In calorimetry, we create an isolated system. Right? So our system is contained within the styrofoam cups, in this case, and no energy is allowed to transfer in or out. Okay? So, in order to measure the heat, we need to know some things. First of all, what do we mean by heat capacity? Right? Heat capacity is energy required to change the temperature of an object by 1 degree Celsius. Okay, it's usually measured in joules. Now, that being said, if you have a larger object, it's going to take more energy to do that, right? And so heat capacity is a capacity factor. It changes with the amount. But if we divide the heat capacity by the amount of the material being measured, we get an intensity factor that does not vary with the amount. We ratio the two. So if we divide that by the mass of the object, then we get specific heat capacity. And that's the same definition except for energy required to change the temperature of, down here, to change the temperature of 1 gram. So, yeah. I want to check to be sure because standard measure is kilograms, but we're using 1 gram. The temperature of 1 gram of substance by 1 degree. So we just took this value and divided by the mass of the object that we measured, and that gave us specific heat capacity. Now, specific heat capacities, they're listed in manuals. Right? You can find them for thousands of materials. So you can use that information in the calculations that I'm going to show you in a minute. This is specific heat capacity. It's in terms of 1 gram of substance. The molar heat capacity is similar to specific heat capacity, only it's based on 1 mole, not 1 gram. Okay? And in many respects, it's more useful because we know when we're comparing moles of 2 or more substances, we're actually comparing numbers of those substances. So the molar heat capacity is based upon 1 mole, not 1 gram. Otherwise, everything else is the same. Okay. So if we put 2 reactants, put 2 things in our calorimeter, and we measure the temperature before and we measure the temperature after they've mixed, and we see an increase in temperature, that means the reactants have done something and it gets warmer. In that case, we have an exothermic reaction. If they got cooler, it would be an endothermic, right? And if you work in a hospital environment, sometimes your patient needs one of those warm packs. Right? Just a plastic bag filled with water and some chemical. And if you break the thing containing the chemical inside and shake it up, it's warmer. Right? So the reaction, actually the heat of solution, that stuff goes into aqueous solution and in the process releases heat. That's exothermic. But you've also got one on the shelf that's endothermic, a cold pack. So you break it, And it's got a different substance in there that goes into solution. And when it does that, it absorbs heat. That's an endothermic reaction. Heat of solution. Okay, so this is what our calorimeter is going to look like. We've got styrofoam cups. In fact, we use 2 of them just to be absolutely sure that our calorimeter is isolated. Right? No heat transfer across that boundary. And then everything that we conduct in this experiment is inside here. And we measure the temperature with that thermometer. And we might use a stirrer. Actually, I've eliminated the stirrer from our procedure. We're going to leave that out. We just use the thermometer and move it around. That stirs things. Now, what formula is useful here? Well, Q still means heat, right? So our Q for a substance, for instance, like water, carries with it a specific heat capacity, right? But whatever that happens to be is a value there. And it's in terms of joules per gram degree centigrade. So it'll change this number, this heat of that object changes relative to how many degrees in temperature it changes and relative to 1 gram. Okay? So we multiply that times the mass of that substance. This is in grams. So this is in the denominator, that's in the numerator. They cancel. So at this point, we're left with joules per degree centigrade because we've taken out the factor of mass. Then we need a change in temperature. So a change in temperature factors out this one. Now we're left with joules over here. Okay? So that's your formula for any substance that for which we know the specific heat capacity, we know its mass, and we know the temperature change. So this is like any formula. If you know all but one, you can solve for the unknown. Right? And this actually is 2 values, right? Final temperature minus initial temperature. So I actually have 1, 2, 3, 4 here. So if you know all of these, before and after temperature, mass, and specific heat capacity, you can calculate the amount of heat that was transferred. And depending on this value, whether this is bigger or that's bigger, this will be a negative or a positive value. Okay? Okay. So let's do some sort of, oh, we're into lab time, aren't we? Okay. Does anybody need to take a break?
I do.
Good, okay. Let me pause it. Remind me to start it up again. This one should be fairly easy to intuit. If you have 100 grams sample of water at 90 degrees centigrade, you mix it with another 100 gram sample of water at 10 degrees, right? What do they have in common? Well, they're both the same mass, and they're both the same specific heat capacity. We don't need to know what it is, because they're both the same. So if they're both starting out, one is at 90 degrees, the other at 10 degrees, what's going to be the combined temperature? Will it be higher than that, or lower than this, or somewhere in between? Right. In fact, since they're equal amounts, it's going to be exactly in the middle. So 90 minus 10 is 80 degrees. So that's the difference, split the difference is 40 degrees. So you can move 40 degrees from either end. 40 plus 10 is 50, or 90 minus 40 is 50. So it should end up at 50 degrees. Okay. But what if you have different amounts at the 2 temperatures? What do you do? Well, let's take it qualitatively first. We've got 100 grams at 90 degrees and 500 grams at 10 degrees. So is it going to be greater than or less than 50? We know it won't be in the middle. It's probably going to be closer to the one with the more mass. Right? So the 500 degrees is 10. So it should be between 10 and 50, on the low end. So how do we calculate the final temperature of the water? All right, here's how you do it. Remember our isolated system does not allow energy to go in or out. So everything that happens in Vegas stays in Vegas, inside the cups, right? So that means any changes that occur are zero, because nothing's getting out, nothing's going in. There's no change internally. So whatever we do inside that isolated system has to equal zero. So in this case, we have some heat related to the heat related to, let's see, first hot water, right? And the heat related to the cold water. So both of those added together, whatever happens to them, heat, whatever, has to equal zero, because it's isolated system. So now what we need to do is calculate what are these two, all right? So we have this for water, and we have the mass of the water, and we have the change in temperature for that. And then we also have the same thing happening for the other one, right? So, let's see. Is that going to be, let's see, do I have a slide following that? Yes, I think. But I don't have all the information I need. 4.18. So the S for water is 4.18 joules per gram degree C. Okay. The mass for the hot is 100, right? That's times 100 grams. And what's the change in temperature for the hot? Well, the change in temperature is final minus initial. So what's the final? We don't know what the final is. That's the question. Minus the initial, and it starts off at 90 degrees, right? Okay, so that's the first cube right there. The second cube is also 4.18, because they're both water. But the mass is different, 500 grams, right? And then the change in temperature is also the final minus the initial. In this case, it's 10 degrees with cold water. Okay? And this is all equal to 0. So now we have a formula set up with one unknown. So what do? Well, we factor it out. Right? TF times 100 times 4.18. So 418 here times TF. Right? Minus 418 times 90. Correct? Which is 3762. Okay? That's the first one. The second one is this one times that one times this one. So So 4.18 times 500 is 2090 times TF minus 2090 times 10. 2090. There we go. Okay, so that's still equal to 0. Now what do we do? We collect numbers and coefficients of unknowns. Right? So this one plus that one is what? 418. Is plus. That's not right. Let me do that again. 209. 418. 2508. Both of these are minuses, so just add them together and keep the sign. 209. 3762 is 24662. That's right. Still equal to 0. Right. Now this comes over on this side and becomes a positive, and the final temperature then is equal to that one divided by this one. 9.8. 9.8. Does that make sense? No, it doesn't. What did I do wrong? Let's check our work. That's constant. 100 grams, final temperature minus 90 is initial temperature. Okay. This one, 500 grams, final temperature minus 10. That's right. Okay, so 4.18 times 100 is 418 times this, and then 418 times 90 is 37. That's where I went wrong. 418 times 90 that. Okay? So now, this one stays the same. This one, that value plus 2090. So this should be 58520. Now, how did I know that was the wrong answer? Because it was less than 10, wasn't it? It couldn't be. That's an impossibility. Okay, so this is 5820 divided by 258 is 23. 23. Okay, so that's more realistic. That's between 10 and 50. Rounded off the two places. Okay, does everybody get the gist of this method? Set everything to 0. Now, if you have some other terms out here, it still works. If you can visualize your system as that heat, that heat, that heat, that heat, you can put them all together, but they always have to equal 0. Okay. Everybody still writing? I can wait. Okay.
You can,
Okay. All right. Now, for this one, we have different advantages. For this one, we've got our styrofoam cup, 50 grams of water at 10 degrees. And then we're going to add 50-gram iron ball at 90 degrees to the water. So we've got two different specific heat capacities, one for the water and one for the iron. So we need a Q for the water and a Q for the iron ball. Right? So can we say anything about the final temperature? Well, let's see. The iron ball starting off, it's 50 grams here, 50 grams of water. So it's probably going to be somewhere in between 10 and 90. But is it going to be down here? Or what you need to look at is the specific heat capacity. The water is going to change less for the same amount of heat. That's what high heat capacity means. It takes a lot more heat to change a specific amount by a degree. So it takes a lot more heat to change that water by a degree. So it's going to go up just a little bit from 10. This one's going to go down a lot from 90. So my guess is the temperature is going to be between 10 and 50. The only way to know for sure is to calculate. That's our estimate. Now let's calculate what the actual value is. So the Q for water is 50 grams. Well, let's see, specific heat first, 4.18. I'm going to leave the units out because they kind of clutter things. But if we put everything in there in the proper order and all the right elements, we should be okay. So the mass is 50 grams. I will put that one in there. And then the change in temperature. So the final temperature is whatever. We don't know what it is. The initial temperature for water is 10 degrees. Okay? So that's the water. Now for the iron, we have a different specific heat capacity, 0.45, yeah. Same mass. And then a final temperature. Do we know that's true? Are they going to be the same final temperature? Yeah, it's called coming to equilibrium. When the experiment's finished, the iron and the water are going to be the same temperature because they're both right there together in contact. So the final temperature is going to be the same. The initial temperature for iron is different. There. Okay, now we just have to solve it. All right, so this one times that one is what? So 50. I get 209. 209 times T for that. And then this one times this one times this one, negative. Get 2090. Okay. That one. This one is 50 times 0.45, which is 22.5 times this one. And then this one times that one is 2025. Okay? Now we'll combine our terms. Right. This one combined with that one, 209 plus 22.5. So I get 2 31.5 times T sub F. And then this minus and that minus together. So 2090 and 2025 is 4115. And they're both negative, so this one's negative. Now, so if we move this one over here, it becomes positive, and then we divide it by this one, equals to that value. Let's see, 231.5. I get 17.8. I'll round it off to 18. And that is between 10 and 15. Okay? Have to be methodical. Very deliberate, methodical. You might even want to put what you know down here and then build your equation and fill in the numbers, solve. Whatever it takes so that you don't put numbers in the wrong place. Okay. Now to Hess's law. Hess's law depends on the fact that enthalpy is a state function. And it doesn't matter how you get there. Hess's law refers to a chemical reaction, and we're trying to determine the enthalpy for that reaction, the delta H. But we don't want to have to conduct that experiment like before. So what Hess's law says is, if you can find two or more reactions in the literature where you have delta H's for each one, and you can manipulate them in such a fashion that when you add them together, you get the reaction you're interested in, the target. Then you can calculate the delta H for that target reaction based upon the delta H's for the component reactions that go into it. Okay? It's a summation. All right. So here's an example. We're saying that this reaction, we could do this reaction. Nitrogen gas plus oxygen yields nitrogen dioxide. And we measured 68 kilojoules for that reaction. But if we say that this reaction, our target here, right there, could also be written as this one plus that one. Right? So N2 plus O2 yields NO. And then 2 NOs plus O2 yields 2 NO2s. The enthalpy for this reaction is 180. And the enthalpy for this one is negative 112. If we can add these two together, let's see if we can. Let's see, there's our one nitrogen that comes down. There's an oxygen on this side of the arrow. There's two. This one's on the right here and on the left here, so it cancels. And this one is left over as a product. So all we have to do now is add these two together to get the final one, and it equals to the value that we determined experimentally. So the calculated agrees with the experimental. And that's Hess's law in a nutshell. All you have to do is be sure that when you add these two together, you get the target. If you have to change these in any way to make them do that, then that also changes this value, right? And you need some rules to go by. Well, this is an energy diagram. It just explains how Hess's law works. Since it's a state function, it doesn't matter if we go up and down and up and down and up and down. As long as we end up in the same place, it works. Okay. That's the whole point of that diagram. One-step reaction gets you here. Multi-step by addition gets you there. But the delta H's are exactly the same.
Hess's Hess's law illustrates why enthalpy is a state function. For example, we want to determine the enthalpy change for the combustion of graphite to carbon monoxide. Imagine that the reaction takes place in two separate steps. Step 1 is the combustion of graphite to carbon dioxide. Step 2 is the decomposition of carbon dioxide to carbon monoxide. The net result is obtained by adding the two steps and canceling out like terms. The enthalpy change for step 1 is negative 787 kilojoules. The enthalpy change for step 2 is positive 566 kilojoules. Therefore, the desired enthalpy change for the net reaction is the sum of negative 787 and positive 566 kilojoules, or negative 221 kilojoules.
Okay. Okay, so what do we do if we have to change the reaction? We might have to modify it a little bit. Maybe we have to flip the reaction the opposite direction, like in order for it to add together. If you have to do that, if the reaction is reversed, you just change the sign on the delta H. Right? If it's positive and you flip the reaction, it becomes negative. And that makes sense. Because forward, the reaction is, say, if it's negative, the reaction forward would be exothermic. The reaction in reverse would be endothermic. Positive. Okay, what if you have to multiply by a factor? Say by a 2, or maybe by a 1/2. All you have to do then is multiply the enthalpy of the first reaction before you change it, times that factor. Right? So if you multiply the whole thing through by 2, then you multiply your enthalpy by 2. And once you've got them where you want them, and they add together to your target, then you can add the enthalpies together. So what about this one? Let's see, what are we targeting here? We can use this ammonia decomposition to nitrogen and hydrogen. And notice we've got fractions here. So forget what I said earlier. Whole numbers are desirable, but not always useful. So in this case, we're going to use fractions. And the enthalpy change here is endothermic. Okay. React hydrogen and oxygen yields water, so that's extremely exothermic. Space shuttle engine. Now we want to get to here, right? Okay, what's wrong with this picture? Well, we need nitrogen on the other side, over here. Plus, we need 2 of them, right? So what times this will give us 2 nitrogen? 4. Multiply the whole thing through by 4. It gives you 2 of these, 4 of those, and 6 of these. And then you multiply this times 4. But you also have to invert it. So that positive value you just calculated becomes negative, right? Because you need nitrogen on this side, over here. So you have to do 2 things to that one equation. What about the other? Well, let's see. We need water on this side, so we're going to have to change that to positive. But we also need 3 times as much water, 2 to 6. So we multiply, we invert the reaction and multiply the whole thing by 3, which means we change the sign positive and multiply that by 3. Then when we add them together, we should get the final reaction. Oh, problem solving technique. Start with your target, right? Find out what your target reaction is and work backwards. That'll tell you whether you can use a different reaction, because you have to be able to add them together, and you can't have any new elements or compounds. The ones that are not in the target reaction have to cancel out. So then we reverse and multiply as needed. In this case, right, we're going to multiply that one by 4 as before. We're going to multiply this one by 3. And we've already inverted them, right? So the sign changed. We inverted this one, so the sign changed. Multiply by 3. And now we have this, and we need to add it together, right? So we've got 3 waters here. We got 4 ammonias there. We got 6 hydrogens, which cancel these 6 hydrogens, so they're out. We've got 2 nitrogens there. We got 6 waters. So the only one that had to cancel was the hydrogens. And then we just add this value together because we multiplied them, we changed the signs, now we can add them together. Okay. New concept. Standard enthalpy of formation. What do we mean by that? It's always this way. Delta H. Standard has that little 0 up there. Right? So the conditions are standardized. And then this refers to the formation. So what are standard conditions? Well, for gases, remember, standard temperature and pressure was 0 degrees centigrade and 1 atmosphere. Standard conditions for this are 25 degrees centigrade and 1 atmosphere. And if you have any aqueous solutions or solutions of any kind, they have to be 1 molar, 1 mole per liter in the process. Those are standard conditions. So that the heat that's either absorbed or evolved in the process under these conditions, and the formation part means that the compound is formed from elements in these standard states. Right? So what you do is you start with the compound as your product. So let's do ammonia. How about that? You start with 1 mole of the product, and its standard state, 25 degrees, 1 atmosphere, and concentration doesn't count. It is a gas. Right? Under those conditions, that's a gas. Now, you work backwards. At this point, you can't change the coefficient on that. It's always 1. Okay? So you have to change the coefficients on the reactants, and the reactants are elemental. We form this from the elements, right? So we have nitrogen, and what is nitrogen under those conditions? It's diatomic, and it's a gas. And hydrogen is also diatomic, and it's a gas under these standard conditions. Okay. Now we put coefficients in here, and fractions are okay. In fact, there's no avoiding fractions. So we use fractions here to give us the number of atoms we need on the other side. Let's do this one first. It's easier to understand. So how many you need over here? You only need 1, right? So you need half of that to give you 1 over here. Okay. How many of these do you need to give you 3 of those? Three halves, right? Because a half of a 2 is a 1, and a 1 times a 3 is a 3. Okay? So that would be the reaction that would give you a number for the standard heat of formation. So then when you look up the standard heat of formation for that in your book, this is what it means. It may only say the standard heat of formation of ammonia is that value, and it won't give you this. You've got to be able to write that in order to use it in Hess's law, for instance. Okay? Let's see if we got examples here. Okay, so these are the standard conditions. Pure substances are either liquid or solid, and the gases are always at 1 atmosphere pressure, and solutions at 1 molar. For an element, whatever that form happens to be, 1 atmosphere and 25 degrees. Let's see. So what do we got here? Actually, we have a reaction here. CH4, that's methane. Burn methane and oxygen, yield CO2 and water. Now, here's where this is useful. If you know the standard enthalpies of formation, and you have a reaction here, like that, means that 2. And here, we're going to use this example. CO2 plus 2 water. That would be liquid under these conditions. Now, in order to calculate the enthalpy for this reaction under standard conditions, all you need is the standard heats of formation of this plus this. So the enthalpy for CO2 plus the enthalpy for water. And you have to use the coefficients times each one. So this would be 1 times that one. This would be 2 times that one. Okay. And then you subtract the products minus the reactants. So CH4 would be standard enthalpy for methane. There's only one of them. And then we add together whatever it is for oxygen. There we go. Now, remember what I said? Compounds have standard enthalpies of formation. Elements don't. So this one becomes 0. All elements are 0. Right? So that's why this value right here, wait a minute, backwards, negative. Why don't I put those together backwards? Oh, I know what they're doing. Okay, okay. They're keeping them in line with the reaction, like that. But when you actually calculate them, you add up the products and subtract the reactants. Okay? That's why it looks backwards here. Products minus reactants, and don't forget the coefficients. Because the standard enthalpies of formation are always relative to 1 mole of product, of the compound. Right? So if you have more than 1 in your reaction, you have to multiply it by that coefficient. And that way, you can just look these up in a table, ignore that one, add these together, 2 times that one, 1 times that one, subtract this one, and you have the standard enthalpy of that reaction. Okay? This is another way to look at it. Right? Remember, you know what sigma means? Big sigma means summation. Right? So we're going to sum all of the product heats of formation minus the sum of all the reactant heats of formation. And then we stick this little n in there for this coefficient for each one. All right, so that'll vary. That's just another way to express the calculation. Okay. So if we do this one, we're going to take 2 times sodium hydroxide at 1 molar, and that's 0, right? And then we're going to subtract 2 times this one, right? So that's 2 times that, plus it makes it positive because we're subtracting it. And that one's 0. So we just calculated the standard enthalpy for this reaction. Sodium plus water gives sodium hydroxide plus hydrogen, and copious amounts of heat. So if you throw a big block of sodium metal into your neighbor's swimming pool, and it's concrete bottom, it'll probably crack it. Because the reaction is extremely violent. Now, if you want an explosion to go along with it, don't use sodium. Use potassium. It's more reactive. Makes more heat. And all that heat then is sitting there just waiting to ignite the hydrogen. When it combines, bubbles up and combines with air, then the heat from the reaction, bam, you get a big boom. But don't try this at home. Especially now that there are witnesses. And I never told you to do that. Ooh, it's recorded. Okay. So I think we're close to the end now. Sources of energy. We'll just do a cursory discussion. For the longest time, as man was coming up through civilization, his primary source of energy for cooking and for heating and later for smelting iron ores, not just iron, but ores, was wood, right? So he cut down all the forests, right? Well, it's a different reason. They say that Spain, the Iberian Peninsula, used to be covered with forests, just like the United States, right, before we cut down all the trees. But they used the wood for both smelting and for building the Spanish Armada before they hopped on their boats and went off to do battle with England. You know what happened to their ships, right? In the English Channel. Big storm rolled up and sunk them all. Blew them off course, sunk them all. They had to go all the way around Scotland to get home because the British were sitting there and said, you come this way, we're going to sink you. So they had to go, with the storm, they had to go around, and they lost most of their ships. Anyway, wood was the primary source of energy. And then when fossil fuels were discovered, let's see, peat was common in England, right? And cow dung also they used. They can still do in certain parts of the world. Third world, they use dried dung to cook their meals. But when we discovered fossil fuels, in other words, hydrocarbons primarily that are buried in the ground for millions of years and go through conversion, they produce either coal, right, if it's a solid, or petroleum, oil, if it's a liquid, or natural gas, right? And for the longest time, those were the primary sources. That fueled the Industrial Revolution, fossil fuels. And then we discovered that you could, once we learned how to generate electricity efficiently using the dynamo, we managed to harness hydroelectric power. Now, hydropower was being used before then, right? Water mills were used to drive machinery in factories, especially in New England. They used them a lot. And they positioned their factories right next to a stream. And as the water who buy it, turn the wheel, and they have belts running inside and making all their machines run, looms and so forth. But once we learned how to convert water power into electricity, then we built these big dams and put our turbines down there, and the turbines would spin under the pressure of that water and spin and generate electricity, and we can distribute it everywhere. We had to decide how to distribute it, though. Right? Edison said direct current. Right? You could only go a couple miles with direct current before it became a problem, overheating and decrease in voltage. So along came Nikola Tesla, who worked for Edison for a while until Edison screwed him, and he said, "Okay, I'm leaving." And he went and found George Westinghouse. And his idea was to use alternating current, because you could use alternating current to convert low voltage to very high voltage, and that would travel long distances. And then when you get to the other end, you step it back down. Right? So alternating current won out. That's what we use today. And hydroelectric power, the problem with hydro is your number of places that you can build a dam and generate hydroelectricity are limited. Right? Once you've exploited them all, that's it. Right? And then there are other problems with hydroelectric. When you build a dam, you stop a fast-flowing stream, turn it into a slow-flowing stream, so when it brings its sediment load into the backwaters, as it slows down, the sediment goes and starts filling up your lake with sediment. Right? So eventually you either have to, they do what they do at the Summersville Lake. You ever seen it when it's drained? They empty the lake. It's weird. You just drive around that thing and say, look at that big hole in the ground. They let all the water out so they can go in there and excavate the sediment and move it out to maintain the capacity of the lake. And then they let it fill back up. But that's the way that the Tennessee Valley was dotted with dams. And we electrified the Rural Electrification Administration, REA, was used to create the Tennessee Valley Authority and electrify rural Tennessee and northern Georgia and southern Kentucky and parts of Alabama with hydroelectric power. And then we have these big projects, like Hoover Dam, which supplies all the electricity for Las Vegas, which is just down the road. And then the Northwest, which is a temperate rainforest, really. I mean, it rains there. Just the only place that rains more for the United States than Hawaii is Washington State. So they got lots of water there, and they built some pretty big dams. And besides silting in, you disrupt the migration path for certain animals, like the salmon. Right? So they had to build into those dams these special ladders, just little tiny dams that come so the fish can jump over into this one and rest a minute, then jump over into this one. Eventually they make it to the top, and then they can go spawn. So that's wood, hydro, fossil fuels. Then along came nuclear energy, right? The advantage to nuclear energy is once you have a certain amount of fuel, it lasts a long time, like decades, 20 years, before you have to refuel. The problem is it creates waste. So what do you do with the waste? There's always, every solution has a potential problem. Right? So these global warming hysterics that want to do away with all our fossil fuels, right, crash our economy in the process, all you have to do is ask them one question to see if they're really serious. If you're serious about this global warming thing, then what's your opinion of nuclear power? Because nuclear power produces no carbon dioxide. If they're against nuclear power, then you can stand up to them and say, you're a liar. You don't really believe in global warming caused by man and CO2. Otherwise, you'd be for nuclear power. to give you a loaded gun or any hysterics that get in your face. Okay, so this is just the natural course of things. We started off with wood back in the late 19th century and transitioned through the Industrial Revolution to coal and other fossil fuels. And now fossil fuels still are largely the driver of our economies, right? Because cheap energy is the only way to maintain economic growth. If you don't have cheap energy, then your economies collapse. What is it about the Earth's atmosphere? Well, it is true that energy coming from the sun easily penetrates the Earth's atmosphere. There's just a few bands, wavelength bands, that are absorbed in the upper atmosphere by ozone. Those are the dangerous UV rays. Right? So we do want that ozone up there. But everything else comes down and strikes the Earth. And when it strikes plants and surfaces, whatever, it re-radiates usually at a longer wavelength. Right? And the longer wavelength that's re-radiated is absorbed by certain molecules in the atmosphere. And that produces what's commonly called the greenhouse effect. It traps that energy. Now, that's not a bad thing, right? If it weren't for that, the Earth would be a snowball. Right? All that energy coming in. There's not enough energy being generated from inside the Earth to keep the Earth warm enough for life. Right? So the greenhouse effect is a good thing. When you consider what are the molecules that absorb this energy to keep it trapped in our atmosphere, there are two things to consider. What's its specific absorptivity? Right? How efficient is it? Well, there are things like carbon dioxide and water. There's lots of water in the atmosphere. And other things that we've added along the way, like chlorofluorocarbons, like freons, and methane. Right? So we can add methane to the atmosphere. And of course, cows add a lot of methane when they belch, because in their rumen, they've got these microorganisms breaking things down. One of the byproducts is methane. So when they belch methane. When we belch hydrogen. But the specific absorptivity is relatively low for carbon dioxide. It's much higher for methane. And I'm not sure what it is for water. But the second factor plays more for water, because our atmosphere is just saturated with water. Water is the major energy absorber for the greenhouse effect. Okay? Unless it's in the form of clouds. And then it reflects the energy before it even gets to the surface. Okay? So all that being said, the models that are proposed for global warming, you know, they say like we're going to heat up 2 degrees in the next century. The problem with that is that the atmosphere is just way, way too complex to model efficiently. And the evidence for that is that none of the models work. Not one of them. Not a single model predicting global warming works. They make it work. They force it to work by fudge factors. They tweak it to give them the answer they want. So that's why I've got that Gilbert cartoon on my window, my door. Right? The guy in the beard is supposed to be Michael Mann, you know, the hockey stick guy. You know about the hockey stick? Yeah. He said that over time, the temperature of the Earth was like very stable for the longest time. And then when man started burning fossil fuels, it went like that. Right? What he doesn't tell you is that he threw out some anomalies in there, like the medieval warm period or the little ice age. He just threw those out and said, this is my pretty graph. Don't argue with me because I'm a college professor. Right? Well, people did argue with him, showed him to be a fraud, and now he's in hiding. But that cartoon makes fun of him. And word has it that when he first saw that cartoon, he hit the roof because he knew it was making fun of him. Anyway, so the end result is, yeah, the atmosphere, I mean, the climate does change over time. We know that from the fossil record. Right? There was one time when the Earth was a snowball, right? Or there were times in the Earth's history when it was basically a sauna. The whole globe was a sauna. Those are the time periods when it was a sauna, when lots of carbon dioxide was being fixed in plants, so much so that they couldn't be recycled efficiently. So they got buried. And that's where our fossil fuels come from. Right? There's also evidence, scientific evidence, that if the Earth warms and we produce more CO2 and release more into the atmosphere, plant productivity will increase. Right? Because CO2 is plant food. That's what they use to make their biomass. And they do it more efficiently at higher temperatures. Well, not all of them, but a lot of them do. There's controversy, I mean, not controversy, there's the difference between C3 type plants and C4 type plants and crasulation type plants. So I won't get into that. But they have different biochemistries. C3 plants are more efficient at higher temperatures. Anyway, so if you want to know more on that subject, there are a number of people who are derogatorily called climate deniers. Right? They're actually scientists who study this stuff and can give you a reasoned argument based on evidence for why we shouldn't panic. Okay? Why we shouldn't wreck our world economy just to line the pockets of Al Gore and his buddies. Because that's what they're doing. Right? They form these exchanges, right? And they're making lots of money off of it. So naturally, they want to increase the panic. There's one guy, he's retired now, Richard Lindzen, Lindzen. He's a climatologist for, I think the last place he worked was a college in upstate New York, Troy. Escapes me right now. Anyway, he's published some really good work, and he was not one of the signatories to the IPCC, the group that publishes periodically these hysteric reports on behalf of the UN. Okay, new energy sources. Well, actually, economic forces are already driving the production and use of low carbon emission sources, which is fine. If the economy can support it, go ahead. If you can make money at it, that's a capitalist way. Coal conversion. So they're making natural gas out of coal, and they're taking a lot of the pollutants out and process the ash, the sulfur, right? Hydrogen as a fuel. If we can ever get a cheap enough source of energy and the infrastructure to use it, hydrogen would be a good source of energy, because what do you get? Hydrogen plus oxygen is water. That's it. Right? No other product. Hydrogen is also good. It's also a potential fuel for fuel cells. Right? The problem with batteries is once you charge them up, eventually they discharge. You got to recharge them. With a fuel cell, all you have to do is keep the fuel going through the cell, and it makes electricity. It's like your engine in your car. The only time you stop is when you run out of gas. So a fuel cell will be the same way. If you run out of hydrogen, then the fuel cell will stop. But if we have the infrastructure, that's the problem. We don't have infrastructure for distributing hydrogen to vehicles. But it's very efficient at producing electricity. Other alternative sources, and we're tapping these now. Oil shales, with fracking, we get access to oil in underground deposits that we had previously abandoned. We couldn't get at it. But fracking opens those up. It also opens up lots of natural gas. In fact, the U.S. is a net exporter of natural gas now. We're energy independent. And I might add, thanks to Trump and his policies. Ethanol, right? Basically made from corn in this country. Takes more energy to make a gallon of ethanol than it does to the energy that's contained in the corn. Right? So it's a net negative. The only reason that ethanol from corn is still available is because the government subsidizes it. If it doesn't subsidize it, they go out of business tomorrow. Ethanol, they make ethanol in Brazil, but they make it out of sugar cane. Right? Same thing. It's subsidized. So, and there may be a strategic reason for them to do it. Right? You have to import oil from outside the country, then you're at the mercy of other countries, like we were in the 70s with the OPEC oil embargo. Now we don't have to worry about that. Methanol is another source, and these can be generated from biomass, right? That's the holy grail for making ethanol. If you can make ethanol from biomass rather than from the seed from corn, right, you're throwing all that stalk away. If you could use all that biomass to make ethanol, then it might become economically viable. And besides, there are other things more efficient, that grow more efficiently than corn, that could be used to make ethanol. And then there's seed oils. Those are not much more. The seed oils you could use in diesel engines. Right? I forget the guy's first name, Diesel, that invented that type of engine, actually designed it to run on vegetable oil. And we only converted later into running on fossil fuel, diesel fuel. So you could burn oil in it. Works pretty well. Trouble is with oils, you have to preheat them. They're not designed to vaporize efficiently. So if they're heated before they go into your engine, then it works better. Okay. That's all I have to say about that. Channeling Forrest Gump.